In this video I'm going to show you how to do Edexcel A-Level Maths June 2019 Paper 1 Question 12. My name is Sunil Tanna. I'm a tutor and author. I'm available for one-to-one tuition both online and in person. I live in Buckinghamshire, England. As you can see, question 12 is quite a long question, so it's difficult to show both the question and the solution at the same time. So what I've done is I've cut up parts of question 12 and then it gives me space to write underneath the solution. So let's start. Okay, the first part of question 12 is f of x is equal to 10 times e to the power of 0.25x times sine x, where x is greater than or equal to 0. Show that the x-coordinates of the turning points of the curve with equation y equals f of x satisfy the equation tan x equals 4. Okay, so we have a formula for f of x. So to find the turning points, we need to differentiate. So we need to find f dash of x. Now, f dash of x, when we look at f of x, it's two expressions involving x multiplied together. 10 times e to the power of minus 0.25x times sine of x. So what we do is we use the product rule. We differentiate one expression and leave the other part alone, and then we do it the other way around. And the derivative is those two parts added together. So differentiating the first part, 10 to the power e to the minus 0.25x, that would be minus 0.25 times 10 to the power e 0.25x, and that's still times sine x. And then differentiating the second part, we'll have 10 to the power e to the minus 0.25x, not differentiating that. The derivative of sine x is cos x. So we get this expression, which we can notice that e to the minus 0.25x is a common factor in both parts, and also we can expand out this brackets. So probably the easiest way to write that is f dash of x is equal to e to the minus 0.25x, and then brackets, we've got 10 times cos x, so 10 cos x, minus 0.25 times 10, which is 2.5 sine x. Okay, now we want to find the turning point. So at the turning points, f dash of x is equal to 0. So we'll have 0 is equal to e to the minus 0.25x over 10 times 10 cos x minus 2.5 sine x. Now this part here, e to the minus 0.25x, can never be 0. So the part that has to be 0 would be the brackets here. So as e to the minus 0.25x is not equal to 0, this gives us 0 is equal to 10 cos x minus 2.5 sine x. Now what we want to do is divide both of these by cos x to get us a tan x, because this will be cos x divided by cos x will just be 1, and sine x divided by cos x will be tan. So if we divide the whole thing by cos x, and we can also divide the left-hand side by cos x, which is still 0, we will now end up with 0 is equal to 10 minus 2.5 tan x. So bring the 2.5x sine x to the other side, tan x to the other side, 2.5 tan x is equal to 10. Tan x is equal to 10 divided by 2.5, which is 4, and that's the result we wanted. Okay, now to the next part of the question. Now we're given this graph here, figure 2. Figure 2 shows a sketch of part of the curve with equation y equals f of x, the equation we've just already looked at. Sketch the graph for h against t, where h of t equals the absolute value of 10 times e to the minus 0.25t times sine of t, showing the long-term behavior of this curve, and t is greater than or equal to 0. Now, if you compare this equation to the previous one, f of x, or y, became h, so the y-axis is going to be h of t, x becomes t, and the last thing was that we have the absolute value. So all the values that are underneath in the y direction, these parts of the curve, will be on top. So for part B, the curve is going to kind of look like It's first with the big bump above. So the second bump, which was underneath, will now be on top. The third bump, which was on top, will remain on top, and so on. The fourth one will be a bit smaller on top, and so on and so on and so on. Where the y-axis here is h of t, the x-axis is t. We could also see where it touches the x-axis. If you think about sine of t has to be equal to 0 at these points, so that happens at pi radians, 2 pi, 3 pi, 4 pi, and so on. Okay, so that's part B. Part C says, using this model, find the maximum, the function h of t is used to model the height in meters of the ball above the ground t seconds after it's been kicked. Using this model, find the maximum height of the ball above the ground between the first and the second bounce. So this point here, or if you like, the absolute value of this point here. So we already have an expression for f dash, so that's basically the same expression for h dash, except for we have to, of course, take the we'd have to take the absolute value of h, but it doesn't actually make a difference because in our original the turning points are above and below, but the x coordinate or the t coordinate remains the same in the bounce model. So we know that on this second bounce here, f dash of x would be equal to 0, or h dash of t would be equal to 0, and we know at those points, at any of these turning points, tan of x or tan of t is equal to 4, which is what the result we got in part A of the question. So for part C, really all we have to do is solve tan t is equal to 4. Remember, of course, we're still working in radians. Okay, so we can just do inverse tan on our calculator, and when we do that, we will get roughly t is equal to 1.326, which of course will be the first point here. But we notice that it repeats every pi radian, so it's plus n pi. So between the first and the second bounce, it will, in this case, n is 1, because we're pi radians on from the first bounce. So this gives us t is equal to roughly 4.47. Right, and now what we need to do is put it into this expression for h of t. So h of t, if we put it without the absolute value signs in our calculator, we get minus 3.17. So it's the absolute value of minus 3.17, which is, of course, is 3.17 meters. Okay. Part D, explain why this model should not be used to predict the time of each bounce. Well, this is very simple. If we look at our bounces, they occur at regular time intervals every pi seconds. Of course, if you drop a ball, the first bounce takes a long time because you drop it from a great height. The second bounce takes less time because it only has to go up a little bit in the air before it falls down again. And the bounces get closer and closer together each subsequent bounce. So the reason why we couldn't use this model to represent the time intervals is the time intervals between bounces should decrease, but the model shows them as constant. And that completes question 12.